Q1 over N1 plus P2 Q2 over N2. That's the variance. And therefore, the standard deviation is equal to rad P1 Q1 over N1 plus P2 Q2 over N2. Now, under the null hypothesis, H0, we assume that P1 equals P2. We're assuming that these proportions are the same under the null hypothesis. I'm right here. So why not have some common P, which we're going to call P tilde. So assume that P1 equals P2 equals some common P, P tilde. So under the null hypothesis, the standard deviation of P1 hat minus P2 hat is given by, I'm going to pull out this P tilde Q tilde. Let me replace here. How about this? P tilde Q tilde over N1 plus P tilde Q tilde over N2. The P tilde and Q tilde are common, so let's pull them out. Equals radical P tilde Q tilde rad 1 over N1 plus 1 over N2. So if we are talking about the assumption that P1 and P2 are the same, which is the case under the null hypothesis, then the standard deviation is given by this statement right here. And this expression is what you will find in the denominator of the z-test statistic. I'm right here. In the denominator of the z-test statistic, that's where this comes from. So we have just finished explaining that this is the mean of P1 hat minus P2 hat, and this on the bottom is the standard deviation of P1 hat minus P2 hat under the H0 assumption, meaning given that the null hypothesis is true. Okay, so now we have a test statistic. Let us actually go and do this test. I'm ready to use this 2x2 matrix and hypothesis test to see if these proportions are the same. So my Z0 will be P1 hat, which is 1/4, minus P2 hat, 1/2, minus P1 minus P2 from the null hypothesis. So I'm picking up this number right here, this number 0. P1 minus P2 under the null hypothesis is 0. So this is a 0 divided by radical P tilde Q tilde. So radical P P tilde was 85 over 180 and Q tilde 95 over 180. So 85 times 95 over 180 and 180. Rad 1 over N1. N1 is 20 and N2 is 160. And I compute this number. So in the numerator I have minus 1/4 and I need to find my denominator. So let's do that, please. I have 85 over 180 times 95 over 180. Take the square root of that. So 0.4992277. Radical 1 over 20 plus 1 over 160. So 1 divided by 20 plus 1 divided by 160 and the square root of that. 0.2371708. Let's get this quotient. So minus 0.25 divided by 0.4992277 times the answer. I get negative 2.11. That's my test statistic, Z0. Next, I draw my Z distribution. This has 2 rejection regions. This is a 2-sided test with alpha equals 0.05. So 0.025 here and 0.025 here. I go to the bottom of my T table and I pick up from the Z row the value, the critical values, which are 1.96 and minus 1.96. I looked under the column 0.025. So these are my 2 rejection regions. And I go and I drop this test statistic in this picture and it falls here, minus 2.11. So my conclusion is reject H0, which said that P1 equals P2, in favor of HA, which says that P1 is not equal to P2, and furthermore, because Z0 falls in the left rejection region, we conclude that P1 minus P2 is less than 0, otherwise written as P1 less than P2, which we kind of saw because this P1 here was 1/4 and P2 was 1/2. So it's obvious that P1 is less than P2. And that's what our test shows us also. Let's find the p-value for this. So here's the p-value. I color it in red. The probability of being even more extreme than minus 2.11 and an equivalent region on the other side. So p-value is equal to 2 times norm CDF minus infinity, comma, minus 2.11, comma, 0, comma, 1. So I get second distributions, norm CDF, minus 100, minus 2.11, 0, 1, paste. 0.0174, and of course I have to multiply by 2 still. So I get 0.03485. So 0.0349 is the p-value. P is less than alpha. Reject H naught. Can we find the confidence interval for this? The answer is certainly, because this is a two-sided test. Because alpha is 5%, I will find the 95% CI for mu for P1 minus P2. So find the 95% confidence interval for P1 minus P2. The formula for confidence interval, let's tell you where that is in your notes so you can refer to it, is found on the next page, which is page 20. We're here. It says a 1 minus alpha confidence interval for P1 minus P2 is given by P1 hat minus P2 hat, that's the difference in sample proportions, plus or minus Z alpha over 2 times the standard deviation of P1 hat minus P2 hat. Let me explain it to you here. So this would be equal to P1 hat minus P2 hat plus or minus Z alpha over 2 times the standard deviation of P hat minus P2 hat. Not the standard deviation under the null hypothesis, not this one, but rather this one. P1 Q1 over N1 plus P2 Q2 over N2. This is only in the case where the null hypothesis is true, and we do not assume that when we're doing confidence intervals. So this would be P1 hat minus P2 hat plus or minus Z alpha over 2 times the square root of P1 Q1 over N1 plus P2 Q2 over N2. And since we don't know what P1 and Q1 and P2 and Q2 are, the best we can do is use the sample proportions that we got from our matrix. So from my case here, this answer would be P1 hat 1/4 minus P2 hat 1/2 plus or minus Z alpha over 2, which is 1.96. It's this number right here. Rad P1 hat 1/4 Q1 hat 3/4 over N1, which is 20, plus P2 hat 1/2 Q2 hat also 1/2 over